Cryptography. In this video, we are going to see about cryptography. Cryptography is the science of secret writing with the goal of hiding the meaning of a message. Cryptography is the study of mathematical techniques related to aspects of information security such as confidentiality, data integrity, entity authentication, and data origin authentication. Cryptography is not only the means of providing information security, but rather one set of the techniques. Overview of cryptology. The first thing that we notice is that the most general term is cryptology and not cryptography. Cryptology splits into two main branches: cryptography, cryptanalysis. A number of basic cryptographic tools, that is primitives, used to provide information security. Examples of primitives include encryption schemes, hash functions, and digital signature schemes. The below figure provides a schematic listing of the primitives considered and how they relate. These primitives should be evaluated with respect to various criteria such as level of security, functionality, methods of operation, performance, ease of implementation. Level of security. This is usually difficult to quantify. Often it is given in terms of the number of operations required, that is, using the best methods currently known to defeat the intended objective. Typically, the level of security is defined by an upper bound on the amount of work necessary to defeat the objective. This is sometimes called the work factor. Functionality. Primitives will need to be combined to meet various information security objectives. Which primitives are the most effective for a given objective will be determined by the basic properties of the primitives. Methods of operation. Primitives, when applied in various ways and with various inputs, will typically exhibit different characteristics. Thus, one primitive could provide very different functionality depending on its mode of operation or usage. Performance. This refers to the efficiency of a primitive in a particular mode of operation. For example, an encryption algorithm may be rated by the number of bits per second which it can encrypt. Ease of implementation. This refers to the difficulty of realizing the primitive in a practical instantiation. This might include the complexity of implementing the primitive in either a software or hardware environment. Plain text. In this video, we are going to see about plain text. Plain text is the original message or data that is fed into the algorithm as input. A plain text space peak that consists of all possible plain text. The original message which is to be transferred. It refers to textual data in ASCII format. It is the most portable format because it is supported by nearly every application on every machine. Plain text is the content of an ordinary sequential file readable as a textual material without much processing. Plain text is different than formatted text, where style information is included and binary files in which some portions must be interpreted as binary objects, that is, encoded integers, real numbers, images, etc. The encoding has traditionally been either ASCII, one of its many derivatives such as ISO or IEC, 646, etc., or sometimes EBCDIC. Unicode-based encoding such as UTF-8 and UTF-16 are gradually replacing the older ASCII derivatives limited to 7 or 8-bit codes. Ciphertext. In this video, we are going to see about ciphertext. Ciphertext is the message produced as output. It depends on the plain text and the secret key. The original intelligible message, referred to as plain text, is converted into random text, referred to as ciphertext. The science and art of manipulating messages to make them secure is called cryptography. A ciphertext space C that consists of all possible ciphertext. Ciphertext is unreadable until it has been converted into plain text that is decrypted with a key. The ciphertext is the scheme for encoding messages to prevent them being read by unauthorized persons. It may have been enciphered, encrypted, or encoded, but it all means the same thing. It does not look like English, so no one can use the information unless they have the password or key to decode it. The process of converting the plain text into ciphertext is called encryption. The reverse process is called decryption. The encryption process consists of an algorithm and a key. The key controls the algorithm. A user can recover the original message only by decrypting the ciphertext using the secret key. Depending upon the secret key used, the algorithm will produce a different output. If the secret key changes, the output of the algorithm also changes. Encryption. In this video, we are going to see about encryption. Encryption is the process of changing intelligible data into an unintelligible data. Decryption is just the opposite. For most local area networks, data encryption is used only when the security threat is substantial. Ensuring that data is secure in a network environment is more difficult than ensuring the security of physical documents. Typically, data in network is held in a common storage facility, and anyone authorized to use the central storage has the potential to access classified files. The best solution to this potential problem is to store the data in an encrypted form. Then, any unauthorized person accessing the file would not be able to read its contents. Encryption techniques cover a broad range, from simple encryption that guards against accidental disclosure to sophisticated methods which protect against all but the highly trained criminal with an in-depth knowledge of cryptanalysis and considerable deciphering equipment. Most encryption schemes are based on mathematical operations that are computationally infeasible. That is, they are based on prime numbers which are so large that even the computational power of the mainframe computer cannot break the code within the practical time period. Encryption algorithm. Encryption algorithm performs various substitutions and transformations on the plaintext. Decryption. In this video, we are going to see about decryption. Decryption is generally the reverse process of encryption. It is a process of decoding the data which has been encrypted into a secret format. An authorized user can only decrypt data because decryption requires a secret key or password. Decryption algorithm. Decryption algorithm takes the ciphertext and the secret key and produces the original plain text. Requirements for cryptography. In this video, we are going to see about requirements for cryptography. The basic goal of cryptography is to make the cost or the time required to decrypt a message without the key exceed the value of the information being protected. This is an important concept as it provides one of the basic rationale for selecting cryptographic tools and ciphers. The number of possible keys to a cipher is known as a key space. Without any knowledge of the key, an opponent with access to an encrypted message and the decryption cipher could try every possible key to decode the message. This is known as a brute force attack. By making the key space sufficiently large, it is possible to make the cost of a brute force attack infeasible. Assuming there are no mathematical weaknesses in the cipher, a larger key space usually implies greater security. Ciphers can be either known to the public, that is open source, or hidden from the public, that is closed source or proprietary. The following four form a framework upon will be derived. They are privacy or confidentiality, data integrity, authentication, non-repudiation. Privacy or confidentiality. Confidentiality is keeping information secret from all except those who are authorized to see it. This can be done with a number of techniques including locking safes, posting armed guards, and whispering in someone's ear in a remote field. However, this is often cited as a primary benefit of using cryptography. Cryptography provides confidentiality by rendering information unintelligible to anyone other than those who know the encryption cipher and the proper key. This knowledge may be as a result of being an authorized user or as a result of effective cryptanalysis or theft of cryptographic material. The value of confidentiality is straightforward. Certain communications contain information that could either prove detrimental to the correspondence if disclosed or could prove useful to an opponent. Confidentiality can be achieved by either symmetric or asymmetric ciphers. Both have the capability to encode information and hide it from prying eyes. Confidentiality is a service used to keep the content of information from all but those authorized to have it. Secrecy is a term synonymous with confidentiality and privacy. There are numerous approaches to provide confidentiality, ranging from physical protection to mathematical algorithms which render data unintelligible. Data integrity. The concept of integrity is the protection against unauthorized modification or destruction of information. Data integrity ensures that no party has altered or deleted information after origination. For example, payroll information requires data integrity to ensure that amounts are not modified after being sent to the check printer. Data integrity can be achieved with either asymmetric or symmetric ciphers. Both can provide a level of assurance that information has not been tampered with. Data integrity is a service which addresses the unauthorized alteration of data. To assure data integrity, one must have the ability to detect data manipulation by unauthorized parties. Data manipulation includes such things as insertion, deletion, and substitution. Authentication. Authentication is a service related to identification, This function applies to both entities and information itself. Authentication corroborates the identity of an entity, whether the sender, the sender's computer, some device, or some information. As humans, we instinctively authenticate each other based on physiological characteristics such as facial appearance, voice, skin texture, and so forth. A traditional military authentication mechanism is a password. If you know it, the sentry lets you pass. If you don't know it, you are in trouble. In the digital realm, cryptography provides a mechanism to authenticate entities. Entity authentication or identification can be achieved with either asymmetric or symmetric ciphers. The most straightforward form of digital authentication is a user ID and password. If an opponent can listen in all conversations, including the initial setup where sender and receiver agree on cipher and key, that opponent can masquerade as a legitimate user. Thus, to maintain an ability to authenticate in a symmetric cryptography world, parties must first distribute keys among themselves securely. This is often expensive and time-consuming for a large number of users, but the value of authenticating all parties is sufficiently important in environments that this protection is worth the cost. In an asymmetric environment, authentication is dependent upon a secure public key storage directory. Knowing what secret key was used to encrypt information can provide a means of identification. Asymmetric cryptography offers a more straightforward means of providing authentication, and in fact, it, along with confidentiality, is the cornerstone to electronic commerce on the Internet. Two parties entering into a communication should identify each other. Information delivered over a channel should be authenticated as to origin, date of origin, data content, time sent, etc. For this reason, this aspect of cryptography is usually subdivided into two major classes such as entity authentication and data origin authentication. Data origin authentication implicitly provides data integrity, that is, for if a message is modified, the source has changed. Non-repudiation or digital signatures. Non-repudiation is a service which prevents an entity from denying previous commitments or actions. The security principle non-repudiation can be satisfied with an asymmetric digital signature, but not a symmetric digital signature. If both the sender and the recipient possess the same secret key, one cannot prove to a third party that a message exchanged originated with one party rather than the other. Therefore, the prerequisites for substantiating non-repudiation are as follows. An effective asymmetric key algorithm, a strong hash function, a means to apply the private encryption key to the hash value to produce a digital signature, a tamper-proof or trusted third-party timing device if desired, an agreed-upon protocol for validating digital signatures, a secure key management and distribution system, a public key repository that has an assured level of integrity, key escrow to be able to produce key from parties in case of legal dispute, procedures to handle disputes. Cryptanalysis. In this video, we are going to see about cryptanalysis. Cryptanalysis. Cryptanalysis is the science and sometimes art of deciphering encrypted communications without knowing the proper keys. Cryptanalysis refers to the study of ciphers, ciphertext, or crypto system, that is, to secret code systems, with a view of finding weaknesses in them that will permit retrieval of the plain text from the ciphertext without necessarily knowing the key or the algorithm. This is known as breaking the cipher, ciphertext, or crypto system. You might think that code breaking is for the intelligence community or perhaps organized crime, should not be included in a serious classification of a scientific discipline. Cryptanalysis is central importance for modern crypto systems. Without people who try to break our crypto methods, we will never know whether they are really secure or not. Cryptanalysis is the only way to assure that a crypto system is secure. It is an integral part of cryptology. Breaking is sometimes used interchangeably with weakening. This refers to finding a property, that is, fault in the design or implementation of the cipher that reduces the number of keys required in a brute force attack, that is, simply trying every possible key until the correct one is found. Types of attacks on encrypted messages. In this video, we are going to see about types of attacks on encrypted messages. The various types of cryptanalyst attacks based on the amount of information known to the cryptanalyst are as follows. Attacks of encryption schemes. We can divide attacks roughly into two classes: passive attack, active attack. Passive attack. A passive attack is one in which the attacker is only able to monitor the communications channel. Threatens confidentiality only. Passive attacks can be further subdivided: ciphertext only attacks, known plaintext attacks, chosen plaintext attack, chosen ciphertext attack, adaptive chosen ciphertext attack. Ciphertext only attacks. It attempts to deduce the plain text from the ciphertext only. Less chance to succeed against the strong encryption. Known plaintext attacks. It is the attack that has access to a collection of plaintext messages and their corresponding ciphertext. If same key is used to encrypt multiple blocks, chances of finding the key is possible. Chosen plaintext attack. A chosen plaintext attack is called adaptive if the attacker can choose the ciphertext depending on previous outcomes of the attack. Goal: learn something about other ciphertexts. This can be used to acquire a signed message like "Please authenticate me." Chosen ciphertext attack. Chosen ciphertext attack (CCA) is an attack model for cryptanalysis in which the cryptanalyst gathers information, at least in part, by choosing a ciphertext and obtaining its decryption under an unknown key. The attacker selects the ciphertext, sends it to the victim, and is given in return the corresponding plaintext or some part. Adaptive chosen ciphertext attack. An adaptive chosen ciphertext attack (CCA2) is an interactive form of chosen ciphertext attack in which an attacker sends a number of ciphertexts to be decrypted, then uses the result of these decryptions to select subsequent ciphertext. The goal of this attack is to gradually reveal information about an encrypted message or about the decryption key itself. Active attacks. An active attack is the one in which the attacker attempts to add, delete, or modify messages. threatens both confidentiality and data integrity. Active attacks can be further subdivided: known key attack, replay attack. Known key attack. The attacker obtains previously used keys and uses this to deduce information about new keys. Tracks generation of pseudo-random numbers. Replay attack. An attacker records a communication session and replays part of it at a later time. Login, key exchange. Impersonation. Attacker assumes the identity of one or more members of the network. Reflection attack. A and B want to synchronize with secret keys. A sends a challenge to B. A to M1 to B. B to E of M1, M2 to A. A to M2 to B. Intruder intercepts, pretends to be B, initiating the same protocol. Dictionary. Attacker uses a large list of words to deduce a password. Unix password attacks. Forward search. Brute force search of key space. Consider this authentication protocol. A sends random number M1 to B. A sends M1 to B. B returns random numbers M1 and M2 signed plus an identifier. M2 returns A. B returns SB of M2, M1, A. A returns signed random numbers M2 and M3 plus an identifier. A sends M3, SA of M3, M2, B sends to B. Intent. Random numbers plus signatures will verify identity. An enemy E can initiate two separate protocols with A and B. E sends M1 to B. M2 returns to E. B returns SB of M2, M1, A. E returns M2 to A. A sends M3, SA of M3, M2, B sends to E. E sends M3, SA of M3, M2, B sends to B. Insecurity due to symmetry of messages could vary structure or require M1 to be included in final message. Attacking key exchange. A sends B its public key. Man in the middle replaces A's public key with a false one. Man in the middle is now able to intercept and decrypt secret messages from B to A. Conventional symmetric encryption algorithm. In this video, we are going to see about conventional symmetric encryption algorithm. Symmetric encryption is sometimes called conventional encryption because it preceded the development of newer asymmetric techniques. Symmetric encryption is still the most common form, although public key asymmetric encryption has recently received considerable attention. Symmetric encryption is called symmetric because the decryption process is exactly the reverse of the encryption process. Process of symmetric encryption or decryption are as follows. A secret key is made known to both the sending and receiving computers. The sending computer encrypts the data using a pre-arranged encryption algorithm and the secret key. The encrypted, that is, unreadable text is delivered to the destination computer. Symmetric encryptions can be extremely secure if it is performed carefully. The most important considerations for the security of any encryption scheme are as follows: the strength of the encryption algorithm, the strength of the keys, the secrecy of the keys. Symmetric encryption versus asymmetric encryption. In this video, we are going to see about symmetric encryption versus asymmetric encryption. Symmetric encryption, asymmetric encryption. A single key is used to encrypt and decrypt the data. Two keys are used, one key encrypts the data and the second key decrypts the data. A key is a special word, phrase, or binary number that is used during encryption or decryption to manipulate the data. Asymmetric encryption is generally thought to be more secure than symmetric encryption, as one key is kept private. The single key must be shared between individuals wishing to protect their data. If the key falls into the wrong hands, the encryption data are vulnerable, as anyone with a copy of the key can decrypt the information. The private key is kept private in the hands of a single individual. The second key, called public key, is distributed to anyone who needs it. Even if the public key falls into the wrong hands, no damage can be done with it, as it is only used to encrypt data. Sending and receiving parties to communicate the shared key must be exchanged. A special process is used between the parties to exchange the key. The key length determines the level of data protection provided by the encryption technique. Asymmetric encryption algorithms use two keys to perform the encryption and decryption. Encryption algorithm. Symmetric encryption algorithm key length. The mathematical makeup of these keys allow for each key to decrypt whatever has been encrypted with the other key. This provides for several important capabilities not available with symmetric keys, including digital certificates and digital signature. Between these two encryption techniques, a wide variety of data protection is available. Introduction to block cipher and stream ciphers. In this video, we are going to see about introduction to block cipher and stream ciphers. Cryptographic systems are generally classified into block cipher and stream cipher in analogy to error-correcting codes, which are subdivided into block and conventional codes. Block cipher. Block ciphers encrypt an entire block of plaintext bits at a time with the same key. This means that the encryption of any plaintext bit in a given block depends on every other plaintext bit in the same block. In practice, the vast majority of block ciphers either have a block length of 128 bits, that is 16 bytes, such as the Advanced Encryption Standard (AES), or a block length of 64 bits, that is 8 bytes, such as the Data Encryption Standard (DES) or Triple DES 3DES algorithm. A block cipher is a symmetric key encryption algorithm that is applied to a fixed length block of data, for example 64 or 128 contiguous bits at one time, taking the group as a single unit rather than one bit at a time. The resulting ciphertext is identical in length to the plaintext version of the message. To ensure that identical blocks of text are not encrypted the same way every time they are in a message, making the cipher easier to break, it is common to use the text in one block as a part of the key for the encryption of subsequent blocks, along with the key, to ensure that the subsequent block's encrypting bears no resemblance to the previous blocks. This is called block chaining. The implementation of the block cipher in a grid environment is usually the same as in any other environment in a network. Stream cipher. A stream cipher is a symmetric key cipher where plaintext digits are combined with a pseudo-random cipher digit stream, that is, key stream. In a stream cipher, each plaintext digit is encrypted one at a time with a corresponding digit of the key stream to give a digit of the ciphertext stream. An alternative name is a state cipher, as the encryption of each digit is dependent on the current state. In practice, a digit is typically a bit and a combining operation and exclusive OR, XOR. Stream ciphers are a very important class of encryption algorithms. Symmetric key crypto systems are an important type of modern crypto system. Symmetric key systems are crypto systems where the same key is used for both encryption and decryption. This class of crypto systems is important in modern cryptography because, in general, symmetric key crypto systems are much faster than public key crypto systems. A stream cipher specifies a device with internal memory that enciphers the jth digit mj of the message stream into the jth digit cj of the ciphertext stream by means of a function which depends on both the secret key k and the internal state of the stream cipher at time j. A stream cipher is periodic if the key stream repeats after d characters for some fixed d, otherwise it is non-periodic. Ciphers generated by Rotor and Hagelin machines are periodic stream ciphers. The Vernam cipher, that is one-time pad, is an example of non-periodic stream ciphers. There are two different approaches to stream encryption, such as synchronous method, asynchronous method. Types of stream ciphers. An interesting distinction is made between two types of stream ciphers, synchronous stream cipher and self-synchronizing stream ciphers. A synchronous stream cipher is a cipher where the key stream is generated separately from the plaintext and is then combined with the plaintext later to form the ciphertext. More specifically, a synchronous stream cipher is sigma t plus 1 is equal to f of sigma t comma k, zt is equal to g of sigma t comma k, ct is equal to h of zt comma pt, where f is the next state function, g is the key stream output function, and h is the function that combines the plaintext with the key stream to produce the ciphertext. Note that decryption only requires inverting the h function. The two functions f and g in equation 3 are together known as the key stream generator. The output of these two functions, the sequence of zt values, is known as the key stream. As such, synchronous stream ciphers are also known as key stream can be pre-computed without knowledge of the plaintext of ciphertext. A particularly popular subclass of the key stream generator stream ciphers is the binary additive stream ciphers. In this class of ciphers, the h function is the XOR function represented by XOR. This will be the primary model of stream cipher that will be analyzed. Encryption and decryption with stream ciphers. Encryption, yi is equal to esi of xi, which is congruent to xi plus si mod 2. The plaintext, the ciphertext, and the key stream consists of individual bits, that is, xi, yi, si belongs to set 0, 1. Since encryption and decryption functions are both simple additions modulo 2, we can depict the basic operation of a stream cipher as shown in figure. Note that we use a circle with an addition sign as the symbol for modulo 2 additions. Just looking at the formula, there are 3 points about the stream cipher encryption and decryption function. Stream ciphers properties. The encryption sequence should have a large period. The longer the period of repeat, the more difficult it will be to do cryptanalysis. The key stream should approximate the properties of a true random number stream as close as possible. The more random appearing the key stream is, the more randomized the ciphertext is, making cryptanalysis more difficult. To guard against brute force attacks, the key needs to be sufficiently long. The same considerations as apply for block ciphers are valid here. Thus, with current technology, a key length of at least 128 bits is desirable. With a properly designed pseudo-random number generator, a stream cipher can be as secure as block cipher of comparable key length. The primary advantage of a stream cipher is that stream ciphers are almost always faster and uses far less code than do block ciphers. Block cipher versus stream cipher. In this video, we are going to see about block cipher versus stream cipher. The two major types of symmetric key systems are block ciphers and stream ciphers. Block ciphers in general process the plaintext in relatively large blocks at a time. In practice, in particular for encrypting computer communication on the internet, block ciphers are used more often than stream ciphers. Because stream ciphers tend to be small and fast, they are particularly relevant for applications with little computational resources, for example, for cell phones or other small embedded devices. A prominent example for a stream cipher is the A5 or 1 cipher, which is a part of the GSM mobile phone standard and is used for voice encryption. However, stream ciphers are sometimes also used for encrypting internet traffic, especially the stream cipher or C4. Traditionally, it was assumed that stream ciphers tended to encrypt more efficiently than block ciphers. However, modern block ciphers such as AES are also very efficient in software. Efficient for software-optimized stream ciphers means that they need fewer processor instructions or processor cycles to encrypt one bit of plaintext. For hardware-optimized stream ciphers, efficient means they need fewer gates or smaller chip area than a block cipher for encrypting at the same data rate. However, modern block ciphers such as AES are also very efficient in software. The encryption function is the same for every block. A block cipher can be represented by a function f, which accepts as input a block of plaintext of a fixed size and a key, and outputs a block of ciphertext. F of p, k is equal to c, equation 1. Stream ciphers, on the other hand, process plaintext in small blocks, sometimes as small as a single bit. In contrast to block ciphers, stream ciphers keep some sort of memory or state as it processes the plaintext and uses this state as an input to the cipher algorithm. More specifically, a stream cipher is two functions f and g given in equation 2. Sigma t plus 1 is equal to f of sigma t, pt, k. Ct is equal to g of sigma t, pt, k. Equation 2. F is the next state function which, given the current state, the next block of plaintext, and the key produces a new state. G is the output function which, given the same three inputs, produces a block of ciphertext as output. Note that then next time f and g is called at time t plus 1, the state will be different. Comparison between stream cipher and block cipher. Stream cipher, block cipher. Stream ciphers operate on smaller units of plaintext. Block ciphers operate on larger block of data. Faster than block cipher, slower than stream cipher. Stream cipher processes the input element continuously, producing output one element at a time. Block cipher processes the input one block of element at a time, producing an output block for each input block. Requires less code, requires more code. Only one time of key use. Reuse of key is possible. Example, one-time pad. Example, DES. Application, SSL, that is secure connections on the web. Application, database, file encryption. Stream cipher is more suitable for hardware implementation, easier to implement in software. Data Encryption Standard DES. In this video, we are going to see about Data Encryption Standard DES. Data Encryption Standard DES is a previously predominant symmetric key algorithm for the encryption of electric data. It was highly influential in the advancement of modern cryptography in the academic world. It is most widely used method of data encryption using a private key, that is secret key, that was judged so difficult to break by the US government that was restricted for exportation to other countries. DES adopted in 1977 by the National Bureau of Standards, now the National Institute of Standards and Technology, that is NIST, as Federal Information Processing Standard 46, FIPS PUB 46. The algorithm itself is referred to as the Data Encryption Algorithm, DEA. For DES, data are encrypted in 64-bit blocks using a 56-bit key. The algorithm transforms 64-bit input in a series of steps into a 64-bit output. The same steps with the same key are used to reverse the encryption. The DES enjoys widespread use. It has also been the subject of much controversy concerning how secure the DES is. To appreciate the nature of the controversy, let us quickly review the history of the DES. To accomplish encryption, most secret key algorithms use two main techniques known as substitution and permutation. Substitution is simply a mapping of one value to another, whereas permutation is a reordering of the bit positions for each of the inputs. These techniques are used a number of times in iterations called rounds. Generally, the more rounds there are, the more secure the algorithm. A non-linearity is also introduced in the encryption so that decryption will be computationally infeasible without the secret key. This is achieved with the use of S-boxes, which are basically nonlinear substitution tables where either the output is smaller than the input or vice versa. One of the main problems with the secret key cryptography is key distribution. For this form of cryptography to work, both parties must have a copy of the secret key. This would have to be communicated over some secure channel, which unfortunately is not that easy to achieve. DES uses both the transposition and substitution, and for that reason is sometimes referred to as a product cipher. Its input, output, and key are each 64 bits long. The output of the 16th round consists of 64 bits that are a function of the input plaintext and the key. Advantages: as 56-bit keys are used, there are 70 quadrillion possible key values, and hence a specific key cannot be identified easily. As the length of the key is increased, the security provided by the algorithm also increases. The security of the DES algorithm resides in the key. Disadvantages: as it is a symmetric algorithm, both sender and receiver must have same key. There is a possibility that the key is intercepted. The design of S boxes makes it susceptible to linear cryptanalysis attack. It is susceptible to different cryptanalysis attack and brute force attack, taking advantage of which DES crackers have been designed. It has certain weak keys which generate the same key for all the cycles of the algorithm, like when all key bits are either zeros or ones, or if one half of the key bits are zeros or ones. They are 000, 0000, 000, 000, 0000, 000, FFF, FFFF, FFF, FFFF, 000, 0000, FFF, FFFF, FFF, FFFF. Some initial keys produce only 2 subkeys, while some produce only 4. They are called possible weak keys. DES encryption. In this video, we are going to see about DES encryption. As with any encryption scheme, there are 2 inputs to the encryption function, the plaintext to be encrypted and the key. In this case, the plaintext must be 64 bits in length and the key is 56 bits in length. Looking at the left-hand side of the figure, we can see that the processing of the plaintext proceeds in 3 phases. Key generation techniques. First, the 64-bit plaintext passes through an initial permutation IP that rearranges the bits to produce the permuted input. This is followed by a phase consisting of 16 rounds of the same function, which involves both permutation and substitution functions. The output of the last, that is 16th round, consists of 64 bits that are a function of the input plaintext and the key. The left and right halves of the output are swapped to produce the pre-output. Finally, the pre-output is passed through a permutation IP-1, that is the inverse of the initial permutation function, to produce the 64-bit ciphertext. The right-hand portion of above figure shows the way in which the 56-bit key is used. Initially, the key is passed through a permutation function. Then for each of the 16 rounds, a subkey Ki is produced by the combination of a left circular shift and a permutation. The permutation function is the same for each round, but a different subkey is produced because of the repeated shifts of the key bits. Initial permutation. The 64 entries in the permutation table contain a permutation of the numbers from 1 to 64. Permutation tables for DES. Each entry in the permutation table indicates the position of a numbered input bit in the output, which also consists of 64 bits. Initial permutation IP. Inverse initial permutation IP-1. Expansion permutation E. Permutation function P. To see that these 2 permutation functions are indeed the inverse of each other, consider the following 64-bit input M. Where Mi is a binary digit, then the permutation is as follows. If we then take the inverse permutation, y is equal to IP-1 of x is equal to IP-1 of IP of m, it can be seen that the original ordering of the bits is restored. Single round DES encryption algorithm. The left and right halves of each 64-bit intermediate value are treated as separated 32-bit quantities labeled as L left and R right. As in any classic Feistel cipher, the overall processing at each round can be summarized in the following formulas. Ri is equal to Li-1 XOR f of Ri-1, Ki. Li is equal to Ri-1 S boxes in the function, selecting entry in X box, S box value for DES. The round key KI is 48 bits. The R input is 32 bits. This R input is first expanded to 48 bits by using a table that defines a permutation plus an expansion that involves duplication of 16 of the R bits. The resulting 48 bits are XORed with KI. This 48-bit result passes through a substitution function that produces a 32-bit output. The substitution consists of a set of 8 S boxes, each of which accepts 6 bits as input and produces 4 bits as output. The first and last bits of the input to box SI form a 2-bit binary number to select one of 4 substitutions defined by the 4 rows in the table for SI. The middle 4 bits select one of the 16 columns. The decimal value in the cell selected by the row and column is then converted to its 4-bit representation to produce the output. For example, in S1, for input 011001, the row is 01 row 1 and the column is 1100, that is column 12. The value in row 1, column 12 is 9, so the output is 1001. Each row of an S box defines a general reversible substitution. If you examine the expansion table, you see that the 32 bits of input are split into groups of 4 bits and then become groups of 6 bits by taking the outer bits from the 2 adjacent groups. For example, if part of the input word is E, F, G, H, I, J, K, L, M, N, O, P, this becomes D, E, F, G, H, I, H, I, J, K, L, M, L, M, N, O, P, Q. DES key schedule. The DES key schedule generates the subkeys needed for each data encryption round. The 64-bit key input is first processed by permuted choice 1. The resulting 56-bit key is then treated as two 28-bit quantities C and D. In each round, these are separately processed through a circular left shift rotation of 1 or 2 bits. These shifted values serve as input to the next round of the key schedule. They also serve as input to permuted choice 2, which produces a 48-bit output that serves as input to the round function F. The extra 8 bits were then used as parity, that is error detecting bits, which makes sense given the original design used for hardware communication links. It forms subkeys used in each round and consists of initial permutation of the key PC1, which selects 56 bits in two 28-bit halves. Input key. 16 stages consisting of selecting 24 bits from each half, permuting them by PC2 for use in function F. Permuted choice 1, PC1. Permuted choice 2, PC2. Rotating each half separately, either 1 or 2 places depending on the key rotation schedule K. Schedule of left shifts. DES key generation. 64-bit key is used as input to the algorithm. The initial 64-bit key is transformed into a 56-bit key by discarding every 8 bit of the initial key. From 56-bit key, a different 48-bit subkey is generated during each round using a process called as key transformation. The resulting 56-bit key is then treated as two 28-bit quantities labeled C0 and D0. At each round, Ci-1 and Di-1 are separately subjected to a circular left shift or rotation of 1 or 2 bits. These shifted values serve as input to the next round. They also serve as input to permuted choice 2, which produces a 48-bit output that serves as input to the function f of ri-1, ki. DES decryption. In this video, we are going to see about DES decryption. DES decryption. As with any feistal cipher, decryption uses the same algorithm as encryption, except that the application of the subkeys is reversed order, SK16 and so on up to SK1. Note that IP undoes final FP step of encryption. First round with SK16 undergoes 16th encrypt round, 16th round with SK1 undoes first encrypt round, and then finally FP undoes initial encryption IP, thus recovering original data value. The permutation IP-1 applied to the pre-output block is the inverse of the initial permutation IP applied to the input. Consequently, to decipher, it is only necessary to apply the very same algorithm to an enciphered message block, taking care that at each iteration of the computation, the same block of key bits k is used during decipherment as was during the encipherment of the block, only in a reverse order. For the decipherment calculation, with R10L10 as the permuted input, K10 is used in the first iteration, K10 in the second, and so on, with K used in the 16th iteration. DES weak keys. With many block ciphers, there are some keys that should be avoided because of reduced cipher complexity. These keys are such that the same subkey is generated in more than one round, and they include weak keys, semi-weak keys, demi-semi-weak keys. Weak keys. Weak keys is same subkey is generated for every round, and DES has 4 weak keys. Semi-weak keys. Only 2 subkeys are generated on alternate rounds, and DES has 12 of these in 6 pairs. Demi-semi-weak keys have 4 subkeys generated. Double Data Encryption Standard, double DES. In this video, we are going to see about Double Data Encryption Standard, double DES. Double Data Encryption Standard, double DES. The simplest form of multiple encryptions has 2 encryption stages and 2 keys, double DES. The encryption process could use 2 DES encryption on each block for a given plaintext P and 2 encryption keys K1 and K2. Ciphertext C is generated as C is equal to E of K2, E of K1, P. Decryption requires that the keys be applied in reverse order. P is equal to D of K1, D of K2, C. For DES, this scheme apparently involves a key length of bits, resulting in a dramatic increase in cryptographic strength. But we need to examine the algorithm more closely. Reduction to a single stage. Suppose it were true for DES, for all 56-bit key values, that given any 2 keys K1 and K2, it would be possible to find a key K3 such that EK2 of EK1 of P is equal to EK1 of P. If this were the case, then double encryption and indeed any number of stages of multiple encryption with DES would be useless because the result would be equivalent to a single encryption with a single 56-bit key. Consider that encryption with DES is a mapping of 64-bit blocks to 64-bit blocks. In fact, the mapping can be viewed as a permutation. That is, if we consider all 264 possible input blocks, DES encryption with a specific key will map each block into a unique 64-bit block. Otherwise, if, say, two given inputs mapped to the same output block, then decryption to recover the original plaintext would be impossible. With 264 possible inputs, how many different mappings are there that generate a permutation of the input blocks? The value is easily seen to be 264 factorial is equal to 10,34738,00,000,000,000,000 greater than 10 power 10 to the power 20. On the other hand, DES defines one mapping for each different key for a total number of mappings. 2 power 56 is lesser than 10 power 17. Therefore, it is reasonable to assume that if DES is used twice with different keys, it will produce one of the many mappings that is not defined by a single application of DES. Although there was much supporting evidence for this assumption, it was not until 1992 that the assumption was proved. CAMP 92. CAMP 92. Meet in middle attack. Thus, the use of double DES results in a mapping that is not equivalent to a single DES encryption. But there is another way to attack this scheme, one that does not depend on any particular property of DES, but that will work against any block encryption cipher. The algorithm known as meet in the middle attack was first described in DIFF 77, DIF 77. It is based on the observation that if we have C is equal to EK2 of EK1 of P, then X is equal to EK1 of P is equal to DK2 of C. Given a known pair PC, the attack proceeds as follows. First, encrypt P for all 256 possible values of K1. Store these results in a table and then sort the table by the values of X next. Decrypt C using all 2 power n possible values of K2. As each decryption is produced, check the result against the table for a match. If a match occurs, then test the two resulting keys against a new known plaintext ciphertext pair. If the two keys produce the correct ciphertext, accept them as the correct keys. For any given plaintext P, there are 2 power possible ciphertext values that could be produced by double DES. Double DES uses in effect a 112-bit key so that there are 2 power 112 possible keys. Therefore, on average, for a given plaintext P, the number of different 112-bit keys that will produce a given ciphertext C is 2 power 112 divided by 2 power 64, which is equal to power 248. A similar argument indicates that with an additional 64 bits of known plaintext and ciphertext, the false alarm rate is reduced to 248 minus 64, which is equal to 216. Put another way, if the meet in the middle attack is performed on 2 blocks of known plaintext ciphertext, the probability that the correct keys are determined is 1 to 216. The result is that a known plaintext attack will succeed against double DES, which has a key size of 112 bits with an effort on the order of 256, not much better than 2 power required for single DES. Triple Data Encryption Standard Triple DES. In this video, we are going to see about Triple Data Encryption Standard Triple DES. In cryptography, triple DES. Triple DES is a common name for the triple data encryption algorithm, symmetric key block cipher, which applies data encryption standard DES cipher algorithm 3 times to each data block. This original DES cipher's key size of 56 bits was generally sufficient when that algorithm was designed, but the availability of increasing computational power made brute force attacks feasible. Triple DES provides a relatively simple method of increasing the key size of DES to protect against such attacks without the need to design a completely new block cipher algorithm. Given the potential vulnerability of DES to a brute force attack, there has been considerable interest in finding an alternative. One approach is to design a completely new algorithm, of which several examples are given. Another alternative, which would preserve the existing investment in software and equipment, is to use multiple encryption with DES and multiple keys. We begin by examining the simplest example of this second alternative. We then look at the widely accepted triple DES approach. Triple DES with two keys. Triple DES with two keys is a popular alternative to single DES, but suffers from being 3 times slower to run. The uses of encryption and decryption stages are equivalent, but the chosen structure allows for compatibility with single DES implementations. 3 DES with two keys is a relatively popular alternative to DES and has been adopted for use in the key management standards ANSI X 9.17 and ISO 8732. Currently, there are no practical cryptanalytic attacks on triple DES. Coppersmith notes that the cost of a brute force key search on triple DES is on the order of 2 power 112, which is equal to 5 into 10 power 33, and estimates that the cost of differential cryptanalysis suffers an exponential growth compared to single DES, exceeding 10 power 52. Triple DES must use 3 encryptions, need 3 distinct keys, but can use 2 keys with encryption, decryption, encryption sequence, EDE sequence. C is equal to E of K1, D of K2, E of K1, P. P is equal to D of K1, E of K2, D of K1, C. The decryption of triple DES is in reverse order. There is no cryptographic significance to the use of decryption for the second stage. Its only advantage is that it allows users of triple DES to decrypt data encrypted by users of the older single DES. C is equal to E of K1, D of K1, E of K1, P is equal to E of K1, P. P is equal to D of K1, E of K1, D of K1, C, which is equal to D of K1, C. Encrypt and decrypt equivalent in security. If K1 is equal to K2, then can work with single DES. Standardized in ANSI X 9.17 and ISO 8732. No current known practical attacks. Several proposed impractical attacks might become basis of future attacks. A known plaintext attack is outlined in WANO 90. This method is an improvement over the chosen plaintext approach but requires more effort. The attack is based on the observation that if we know A and C, then the problem reduces to that of an attack on double DES. Of course, the attacker does not know A, even if P and C are known, as long as the 2 keys are unknown. However, the attacker can choose a potential value of A and then try to find a known P-C pair that produces A. The attack proceeds as follows. Obtain n of P-C pairs. This is the known plaintext. Place these in a table sorted on the values of P. Pick an arbitrary value for A and create a second table with entries defined in the following fashion. For each of the 256 possible keys, K1 is equal to I, calculate the plaintext value Pi that produces Pi is equal to D of I, A. Triple DES with 3 keys. Thus, the use of double DES results in a mapping that is not equivalent to a single DES encryption. Thus, many researchers now feel that 3-key triple DES is the preferred alternative, for example, Kali 96. 3-key triple DES has an effective key length of 168 bits and is defined as follows. C is equal to EK3 of DK2 of EK1 of P. Backward compatibility with DES is provided by putting K3 is equal to K2 or K1 is equal to K1. A number of internet-based applications have adopted 3-key triple DES, including PGP and S/MIME. RC4 Stream Cipher. In this video, we are going to see about RC4 Stream Cipher. RC4 is a stream cipher designed in 1987 by Ron Rivest for RSA security. It is a variable key size stream cipher with byte-oriented operations. The algorithm is based on the use of a random permutation. Analysis shows that the period of the cipher is overwhelmingly likely to be greater than 10 power 100. 8 to 16 machine operations are required per output byte, and the cipher can be expected to run very quickly in software. RC4 is probably the most widely used stream cipher because of its simple but effective variable key size byte-oriented operations. It is used in the SSL or TLS secure web protocol and in the WEP and WPA wireless LAN security protocols. RC4 was kept as a trade secret by RSA security, but in September 1994 was anonymously posted on the internet on the Cypherpunks anonymous remailers list. The RC4 key is used to form a random permutation of all 8-bit values. It then uses that permutation to scramble input info processed a byte at a time. Uses of RC4. RC4 is used in a number of applications currently. One of its most important uses is in SSL, also known as TLS, which is used to secure most of the world's electronic commerce over the World Wide Web. It is also used in WEP, the IEEE 802.11 wireless networking security standard. It can also be found in a number of other applications, including email encryption products. RC4 key schedule. The RC4 key schedule initializes the state S to the numbers 0 and so on up to 255 and then walks through each entry in turn, using its current value plus the next byte of key to pick another entry in the array and swaps their values over. After doing this 256 times, the result is a well and truly shuffled array. S forms internal state of the cipher. The total number of possible states is 256 factorial, a truly enormous number, much larger even than the 2048-bit, that is 256 into 8 max key allowed can select. For I is equal to 0 to 255, do S of I is equal to I, T of I is equal to K of I mod key len, J is equal to 0. For I is equal to 0 to 255, do j is equal to j plus s of I plus t of I mod 256. Swap s of I, s of j. RC4 keystream generator. The RC4 keystream generator works by continually shuffling the permutations stored in S as time goes on, each time picking a different value from the S permutation as output. One round of RC4 outputs an n-bit word as keystream, which can then be XORed with a plaintext to produce the ciphertext. Initialization, generation loop, RC4 encryption or decryption. RC4 encryption or decryption. To form the stream key for encryption or decryption, which are identical, RC4 continues to shuffle the permutation array S by continuing to swap each element in turn with some other entry and using the sum of these two entry values to select another value from the permutation to use as the stream key, which is then XORed with the current message byte. I is equal to j is equal to 0. For each message byte mi, I is equal to I plus 1 mod 256, j is equal to j plus s of I mod 256, swap s of I, s of j, t is equal to s of I plus s of j mod 256, ci is equal to mi XOR s of t. RC4 security. RC4 is claimed to be secure against known attacks, have some analysis, none practical. Result is very non-linear since RC4 is a stream cipher, must never reuse a key. Currently, RC4 is regarded as quite secure if used correctly with a sufficiently large key. RC5 stream cipher. In this video, we are going to see about RC5 stream cipher. RC5 is a symmetric encryption block cipher designed by Ronald Rivest. The main feature of the algorithm is that it is very fast. It is parameterized algorithm having a variable block size, a variable key size, and a variable number of rounds. Allowable choices for the block size are 32 bits for experimentation and evaluation purposes only, 64 bits for using a drop-in replacement for DES, and 128 bits. The number of rounds can range from 0 to 255, while the key can range from 0 bits to 2040 bits in size. Such built-in variability provides flexibility at all levels of security and efficiency. The heavy use of data-dependent rotations and the mixture of different operations provide the security of RC5. In particular, the use of data-dependent rotations helps defeat differential and linear cryptanalysis. RC5 objectives. RC5 should be a symmetric block cipher. The same key is used both for encryption and decryption. The plaintext and ciphertext of fixed-length bit sequences, that is blocks. It should be suitable for hardware as well as software. This means that RC5 should use only computational primitive operations commonly found on typical microprocessors. RC5 should be fast. This more or less implies that RC5 be word-oriented. The basic computational operations should be operators that work on full words of data at a time. It should be adaptable to processors of different word lengths. For example, as 64-bit processors become available, it should be possible for RC5 to exploit their longer word length. Therefore, the number W of bits in a word is a parameter of RC5. Different choices of this parameter result in different RC5 algorithms. It should be iterative in structure with a variable number of rounds. The user can explicitly manipulate the trade-off between higher speeds and higher security. The number of rounds, R, is the second parameter of RC5. It should have a variable length cryptographic key. The user can choose the level of security appropriate for his application or as required by external considerations such as export restrictions. The key length, B, in bytes is thus a third parameter of RC5. RC5 should be simple. It should be easy to implement. More importantly, a simpler structure is perhaps more interesting to analyze and evaluate so that the cryptographic strength of RC5 can be more rapidly determined. It should have a low memory requirement so that it may be easily implemented on smart cards or other devices with restricted memory. It should provide high security when suitable parameter values are chosen. Characteristics of RC5. RC5 is suitable for hardware and software and uses only common operations found on microprocessors. It is fast, simple, and word-oriented. Adaptable to processors of different word lengths. The number of bits in the word is the first parameter of RC5. Variable number of rounds. The number of rounds is the second parameter. Variable length key. The key length is the third parameter of RC5. It is easy to implement and analyze. Low memory requirement. Suitable for smart cards or other devices with limited memory. High security. Data-dependent rotations. RC5 parameters. W is the word size in bits. RC5 encrypts blocks of 2 words at a time. Allowed values 16, 32, 64. R is the number of rounds. Allowed values 0 to 255. B is the number of 8-bit bytes in the secret key K. Allowed values 0 to 255. There are 3 routines in RC5. Key expansions, encryption, decryption. Key expansions. In the key expansions routine, the user-provided secret key is expanded to fill a key table whose size depends on the number of rounds. So, for R rounds, there are R plus 2 subkeys. The length of each subkey is 1 word. The key table is then used in both encryption and decryption. The encryption routine consists of 3 primitive operations such as addition, bitwise XOR, and variable rotation. The exceptional simplicity of RC5 makes it easy to implement and analyze. It is easily derived from the encryption algorithm. Cipher modes in RC5. The raw RC5 block cipher. The RC5 takes a fixed size input block, that is 2W bits, and produces a fixed size output block using a transformation that depends on a key. It is the cipher block chaining CBC mode for RC5. It can process messages whose length is a multiple of the RC5 block size. It provides enhanced security compared to ECB. They produce different blocks of ciphertext for repeated blocks of plaintext. It handles plaintext on any length, though the ciphertext will be longer than the plaintext by at most the size of a single RC5 block. It is the ciphertext stealing mode of RC5 which handles plaintext of any length and produces the ciphertext length that matches the plaintext length. RC5 encryption. The input block to RC5 consists of two W-bit words given in two registers A and B. The output is also placed in the registers A and B. Recall that RC5 uses an expanded key table S of 0, 1 and so on up to T-1, consisting of T is equal to 2 into R plus 1 words. The key expansion algorithm initializes S from the user's given secret key parameter K. However, the S table in RC5 encryption is not like an S box used by DES. The encryption algorithm is given in the pseudocode as shown below. A is equal to A plus S of 0, B is equal to B plus S of 1. For I is equal to 1 to R, do A is equal to the rotation of A XOR of B to the left by B plus S of 2I. B is equal to the rotation of B XOR of A to the left by A plus S of 2I plus 1. The output is in the register A and B. RC5 decryption. RC5 decryption is given in the pseudocode as shown below. For I is equal to or down to 1, do B is equal to the rotation of B minus S of 2I plus 1 to the right by A XOR of B. A is equal to the rotation of A minus S of 2I to the right by B XOR of B. B is equal to B minus S of I. A is equal to A minus S of 0. Electronic Codebook ECB mode. In this video, we are going to see about electronic codebook, that is ECB mode. The simplest mode is the electronic codebook ECB mode, in which plaintext is handled 64 bits at a time and each block of plaintext is encrypted using the same key. The term codebook is used because for a given key, there is a unique ciphertext for every 64-bit block of plaintext. Therefore, one can imagine a gigantic codebook in which there is an entry for every possible 64-bit plaintext pattern showing its corresponding ciphertext. For a message longer than 64 bits, the procedure is simply to break the message into 64-bit blocks, padding the last block if necessary. Decryption is performed one block at a time, always using the same key. The ECB method is ideal for a short amount of data, such as an encryption key. Thus, if you want to transmit a DES key securely, ECB is the appropriate mode to use. The most significant characteristics of ECB is that the same 64-bit block of plaintext, if it is known that the message always starts out with certain predefined fields, then the cryptanalyst may have a number of known plaintext ciphertext pairs to work with. If the message has repetitive elements with a period of repetition of multiple of 64 bits, then these elements can be identified by the analyst. This may help in the analysis or may provide an opportunity for substituting or rearranging blocks. Advantages and limitations of electronic codebook ECB mode. ECB is not appropriate for any quantity of data since repetitions can be seen, especially with graphics, because the blocks can be shuffled or inserted without affecting encryption or decryption of each block. Its main use is to send one or a very few blocks, example, a session encryption key. Repetitions in message may show in ciphertext. If aligned with message block, particularly with data such as graphics or with messages that change very little, which become a codebook analysis problem. Weakness due to encrypted message blocks being independent. Main use is sending a few blocks of data. Cipher block chaining CBC mode. In this video, we are going to see about cipher block chaining CBC mode. To overcome the security deficiencies of ECB, we would like a technique in which the same plaintext block, if repeated, produce different ciphertext blocks. A simple way to satisfy this requirement is the cipher block chaining CBC mode. In this scheme, the input to the encryption algorithm is the XOR of the current plaintext block and the preceding ciphertext block. The same key is used for each block. In effect, we have chained together the processing of sequence of plaintext blocks. The input to the encryption function for each plaintext block bears no fixed relationship to the plaintext block. Therefore, repeating patterns of 64 bits are not exposed. For decryption, each cipher block is passed through the decryption algorithm. The result is XORed with the preceding ciphertext block to produce the plaintext block. To see that this works, we can write then Cn is equal to Ek of Cn minus 1 XOR P. Dk of Cn is equal to Dk of Ek of Cn minus 1 XOR Pn. Dk of Cn is equal to Cn minus 1 XOR Pn. Cn minus 1 XOR Dk of Cn is equal to Cn minus 1 XOR Cn minus 1 XOR Pn, which is equal to Pn. To produce the first block of ciphertext, an initialization vector IV is XORed with the first block of plaintext. On decryption, the IV is XORed with the output of the decryption algorithm to recover the first block of plaintext. The IV must be known to both the sender and receiver. For maximum security, the IV should be protected as well as the key. This could be done by sending the IV using ECB encryption. One reason for protecting the IV is as follows. If an opponent is able to fool the receiver into using a different value for IV, then the opponent is able to invert selected bits in the first block of plaintext. To see this, consider the following. C1 is equal to Ek of IV XOR P. P1 is equal to IV XOR Dk of C1. Now use the notation that X of I denotes the ith bit of the 64-bit quantity X. Then P1 of I is equal to IV of I XOR Dk of C1 of I. Then using the properties of XOR, we can state P1 of I dash is equal to IV of I dash XOR Dk of C1 into I. This means that if an opponent can predictably change bits in IV, the corresponding bits of the receiver value of P1 can be changed. It is an appropriate mode for encrypting messages of length greater than 63 bits. In addition to its use, to achieve confidently, the CBC mode can be used for authentication. Advantages and limitations of cipher block chaining CBC mode. The chaining provides an avalanche effect, which means the encrypted message cannot be changed or rearranged without totally destroying the subsequent data. However, there is the issue of ensuring that the IV is either fixed or sent encrypted in ECB mode to stop attacks on first block. Each ciphertext block depends on all message blocks. Thus, a change in the message affects all ciphertext blocks after the change as well as the original block. Initial value should be known to sender and receiver. However, IV is sent in the clear. An attacker can change bits of the first block and change IV to compensate. Hence, either IV must be a fixed value or it must be sent encrypted in ECB mode before rest of the message. Cipher feedback mode CFB mode. In this video, we are going to see about cipher feedback, that is CFB mode. The DES scheme is essentially a block cipher technique that uses 64-bit blocks However, it is possible to convert DES into a stream cipher using either the cipher feedback CFB or the output feedback mode. A stream cipher eliminates the need to pad a message to be an integral number of blocks. It also can operate in real time. Thus, if a character stream is being transmitted, each character can be encrypted and transmitted immediately using a character-oriented stream cipher. One desirable property of a stream cipher is that the ciphertext be of the same length as the plaintext. Thus, if 8-bit characters are being transmitted, each character should be encrypted using 8 bits. If more than 8 bits are used, transmission capacity is wasted. For decryption, the same scheme is used except that the received ciphertext unit is XORed with the output of the encryption function to produce the plaintext unit. This is easily explained. Let Sj of x be defined as the most significant j bits of x. Then C1 is equal to P1 XOR Sj of E of IV. Therefore, P1 is equal to C1 XOR with S of E of IV. The same reasoning holds for subsequent steps in the process. In addition to its use to achieve confidentiality, the CFB mode can be used for authentication. Advantages and limitations of cipher feedback mode, CFB mode. CFB is the usual stream mode as long as can keep up with the input, doing encryptions every 8 bits that is appropriate when data arrives in bits or bytes. A possible problem is that if it is used over a noisy link, then any corrupted bit will destroy values in the current and next blocks, since the current block feeds as input to create the random bits for the next. Limitation is need to stall after every n bits of block encryption. The block cipher is used in encryption mode at both ends. Errors propagate for several blocks after the error in current block. Output feedback mode, OFB mode. In this video, we are going to see about output feedback mode, OFB mode. The output feedback OFB mode is similar in structure to that of CFB. It is the output of the encryption function that is feedback to the shift register in OFB, whereas in CFB, the ciphertext unit is feedback to the shift register. For example, if a bit error occurs in C, only the recovered value of P is affected. Subsequent plaintext units are not corrupted. With CFB, C also serves as input to the shift register and therefore causes additional corruption downstream. Consider that complementing a bit in the ciphertext complements the corresponding bit in the recovered plaintext. Thus, controlled changes to the recovered plaintext can be made. This may make it possible for an opponent, by making the necessary changes to the checksum portion of the message as well as to the data portion, to alter the ciphertext in such a way that it is not detected by an error-correcting code. Advantages and limitations of output feedback mode, OFB mode. One advantage of the OFB mode is that bit errors in transmission do not propagate. Used when error feedback a problem or where need to encryptions before message is available. Superficially similar to CFB, but feedback is from the output of cipher and is independent of message. The disadvantage of OFB is that it is more vulnerable to a message stream modification attack than in CFB. Since OFB is a Vernam cipher variant, the stream should never be used more than once, otherwise the two ciphertexts can be combined, cancelling these bits and leaving a book cipher to solve, and sender and receiver need to remain in sync or all data is lost. originally specified with m-bit feedback in the standards. Subsequent research has shown that only OFB64 should ever be used. Counter CTR mode. In this video, we are going to see about counter, that is CTR mode. The counter CTR mode is a variant of OFB which encrypts a counter value and hence the name. It has been standardized for use with AES along with the other existing 4 modes. It is being used with applications in IPsec, that is IP security. A counter equal to the plaintext block size is used. The only requirement stated in SP 838A is that the counter value must be different for each plaintext block that is encrypted. Typically, the counter is initialized to some value and then incremented by 1 for each subsequent block. Similar to OFB but encrypts counter value rather than any feedback value, must have a different key and counter value for every plaintext block, never reused. CI is equal to PI XOR OI. OI is equal to DES K1 of I. Uses high-speed network encryptions. Advantages and limitations of counter, that is CTR mode. CTR mode has a number of advantages in parallel hardware and software efficiency, can pre-process the output values in advance of needing to encrypt, can get random access to encrypted data blocks, and is simple. In terms of efficiency, can do parallel encryptions in advance of need, good for bursty high-speed links, random access to encrypted data blocks, provable security, good as other modes. But must ensure never reuse key or counter values, otherwise could break. OFB. Comparison of modes. In this video, we are going to see about comparison of modes. Mode, description, typical application. ECB. Each block of 64 plaintext bits is encoded independently using the same key. Secure transmission of single values, for example, an encryption key. CBC. The input to the encryption algorithm is the XOR of the next 64 bits of ciphertext. General purpose block-oriented transmission. CFB. Input is processed G bits at a time. Preceding ciphertext is used as input to encryption algorithm to produce pseudo-random output, which is XORed with plaintext to produce next unit of ciphertext. Authentication and confidentiality. OFB. Similar to CFB, except that the input to the encryption algorithm is the preceding DES output. Stream-oriented transmission over noisy channel, for example, satellite communication. CTR. Key calculated using the nonce and the counter value. Counter is incremented for each block. General purpose block-oriented transmission used for high-speed communications.